Thank you very much. Good afternoon. Thanks for being here for my talk. I'm going to start right off the bat with what I think is the need in the market. So position sensing is a widespread application that you can almost find in any automated integrated systems in most of engineering applications nowadays. So almost in any device that you have today, smart or not smart, you are provided with certain degree of position sensing and proximity sensing. And for us in the sensors business, in general, the good thing is the market for sensors has been on a steady rise, generally has had a steady growth. And specifically speaking, from 2010 onwards, we've seen a big raise in sensors, specifically the ones which are dealing with position sensing, proximity sensing, and the use photonics. And that brings me to the focus of this work. And obviously, that's why I'm speaking about position sensing, because this is the focus of our group. Now, before I get to the work that we have developed in our lab in Fraser, I'd like to speak a little bit about the two main categories for position sensing. So in the literature and in the industry, people usually use discrete position sensing, which is mainly use of grids or arrays of CMOS or CCD detectors, or they use continuous position sensing, which is mainly based on taking advantage of detection of differential ratios in the photocurrent, which is being generated by means of a continuous change in some electrical properties of your sensing material, such as its electrical resistance. Now, both of these methods, both the continuous and discrete in its current state, they're optimized for array architecture. In other words, you have array architecture designs to sense lateral changes in the position of your source of radiation, but we haven't come across anything that enables you to detect the angle of incidence at the same time. And that's why in our lab, our group has developed a new pixel structure, which we refer to as our 3D pyramids pixel. And using this design, we try to address the angular measurement issue that I mentioned in the previous slide. Now, here the responsivity of our device is being defined as the ratio of the photocurrents which is being independently acquired at each facet or either facet of the pyramid, and then putting it through, or first of all, having fixed angle of incidence, having a fixed angle here at the base of the pyramid, and using a simple trigonometry, we can back calculate, using this ratio, we can back calculate the angle of incidence at each pixel. Now, having a system of two pyramids or two pixels then enables us, after calculating the angle of incidence for either one of them, to calculate other quantities, such as the vertical distance between the source of radiation and the plane of detectors, as well as other more sophisticated, I wouldn't say sophisticated, but more computationally intensive parameters, such as the three-dimensional radius of the source of radiation with respect to the array of detectors, and other quantities such as the azimuth of the angle of incidence. So our group, in order to first have a proof of concept, we started off with making a 3D printed prototype and using commercial silicon photodiodes as our sensing material, and a reference bias in order to calibrate our devices, and then outputting the output of the sensor through the filter and all the way into an Arduino board, and passing it through our transimpedance amplifier. We finally used Matlab for our signal processing, and we came up with a very, very interesting result. So when we regress the calculated angle of incidence, the calculated distances or 3D radius between the light source and the center of our pyramid pixels, we came across an R-squared value, which is nearly 0.9. And the reason for that is sometimes we had some measurement issues and outliers. But when we went to our main parameter of interest, which was the angle of incidence itself, we came across, when we regressed it against the actual position values, we came across a value which is significantly high. And that proved our concept that using this technique and using a multifaceted pixel, we would be able to tell or back calculate the angle of incidence of the source of radiation. And then finally, we were able to use our equations and our measured photocurrents in order to back calculate the azimuth of the source of radiation. So for this one, we actually placed our source of radiation in 16 different positions with respect to the pixels. And we passed them through the algorithm, and then we calculated the azimuth angles. And as you can see here, the positions based on the measured value and the actual value is quite nominal. I would say the difference is, I would dare to say, is quite nominal. Now, in summary, using all this data, we'd like to fortify our proof of concept regarding how differential photocurrent measurements in our pixels would allow us to estimate not only the angle of incidence based on a radiation source, but also other additional information such as the azimuth and the distance to the plane of detectors. And the reason we think that this is a very promising technology is because being able to tell which source of radiation at what angle is being approached to your plane of detectors is going to have an enormous impact on industries such as robotics. So therefore, our next step for this work would be to try, and as you can see, it's already not, a roadmap has already started, and we're partially into trying to miniaturize these pixels into the silicon level. And then we've been trying out different recipes for optimizing the shape of our pyramids. A big portion of our group's work have been trying to find out which recipes would best work out to come up with a reproducible recipe for producing these pixels. And well, this was a short present on my end because at the end, I'd like to say that I was presenting this work on behalf of one of our other PhD candidates, Mr. Ibrahim El-chami, who isn't here today. And if you have any questions, I'd be ready to answer them.